Alrighty, everybody. So let's talk about metabolism and energy balance. Okay? So we're going to talk about appetite satiation, energy balance, metabolism, fed versus the fasted state of metabolism, some homeostatic control of metabolism, and we'll end with regulation of body temperature. Okay? So the control of food intake, right, is going to be a very complex process. We have two competing behavioral states. That's your hunger or your appetite and your satiation, right? But it's the hypothalamus. It's that hypothalamus that's right here, as we can see. We always talk about the hypothalamus. It contains two centers. It contains the feeding center, which is tonically active, right? And it contains that satiation center, right? Which basically inhibits that feeding center, right? So it stops food intake, okay? And so we're going to talk about appetite, satiation, and hunger, things like that, right? So there are two theories that will explain like hunger, basically, right? And so we have the glucostatic theory, right? And so the glucostatic theory states that glucose metabolism by the hypothalamus centers regulate food intake. And so when blood glucose concentrations decrease, the satiation center is suppressed and the feeding center is dominant, right? So when glucose metabolism increases, the satiation center inhibits the feeding center, okay? And then we also have the lipostatic theory, right? So that lipostatic theory of energy balance proposes that a signal from the body's fat stores to the brain modulates eating behavior so that the body maintains a particular weight. So if fat stores are increased, eating decreases, right? And so in times of starvation, eating increases. However, obesity, right, will result in a disruption of this pathway, okay? And so it was 1994, right, discovery of leptin, which is a protein hormone synthesized by adipocytes, right? It provided evidence for the lipostatics theory. And so leptin, as you can see here, right, it's going to act as a negative feedback signal between adipose tissue and the brain, okay? You can see there. And so as fat stores increases, adipose cells secrete more leptin and food intake decreases, okay, as we can see right here. So leptin is only part of this lipostatic theory. Another key signaling molecule is this neuropeptide Y that we can see right here, okay? And so this is a brain neurotransmitter that seems to be like the stimulus for food intake. So when they did studies in normal weight animals, leptin inhibits this neuropeptide Y in a negative feedback pathway, right? However, there's other neuropeptide hormones and adipokines that's also going to influence this neuropeptide Y secretion. However, leptin released by adipocytes in the hypothalamic centers, they're going to control that food intake, right? So, energy is going to be stored in fat and glycogen. Glycogen, we know, is just simply glucose polymers. It's going to be stored in the liver and in skeletal muscles. Fat is a compact storage, right? So fat has more than twice the energy content of an equal amount of carbohydrates and proteins, right? And so energy in fat is harder to access, but it's harder and slower to access, okay? But you do get twice as much energy, okay? However, we know that glucose is going to be the preferred energy source because it's quick, okay? So there's going to be many factors that will influence an individual's metabolic rate, and so we can measure that. So typically, the basal metabolic rate is an individual's lowest metabolic rate, right? Typically, that's going to be lowest when you're asleep, right? However, because we can't test it while you're asleep, we test the resting metabolic rate, okay? And that's typically going to be like after 12 hours of fasting and in low energy activity. So then they'll test your resting metabolic rate to get a individual's basal metabolic rate, basically. And so there's going to be 6 factors that affect metabolic rate: age and sex, right? So males at birth will have a higher basal metabolic rate than females at birth, and it's typically because the women, right, they're gonna have more adipose tissue and less lean muscle. And also with age, your basal metabolic rate will decrease, right, as you get older. So if you've been eating the same thing over and over, and as you get older, you notice that you're starting to like increase weight, right? That's because your basal metabolic rate decreases, as you get older. Another factor that affects metabolic rate is the amount of lean muscle mass, an individual's activity level, right? Also diet, right? So your metabolic rate increases after a meal. However, fat causes relatively little diet-induced thermogenesis compared to protein, right? It's going to be harder to break down fat than it is protein. Hormones also play a huge factor, right? And so your basal metabolic rate is going to be increased by thyroid hormones, catecholamines such as the epinephrine and norepinephrine, and there's a genetic factor too that will affect your metabolic rate. Okay, so only the energy intake and level of physical activity, right? Those can be voluntarily changed. You can't change your age or your sex at birth, and you can't change like your genetics or your hormones, okay? However, strength training will typically, right, lead to an increase in lean muscle mass. Easier for some, harder for others, which is fine, right? But this is going to use additional energy and decrease calories going into storage, I should say, right? So what's metabolism? Metabolism is the sum of all chemical reactions in the body, right? So we are able to extract energy from the nutrients. We use that energy for work. And if we have an excess in it, we store that energy, right? And so we want to look at metabolic pathways and metabolic states. So we have anabolic pathways, right? Anabolic pathways are going to synthesize larger molecules from smaller ones. So we're building up. This is going to be in your fed state, right? Or we also call fed state the absorptive state because you're absorbing nutrients, right? And so typically this is going to be the time following the meal, right? So when the products of digestion are being absorbed, used, and stored or build up, right? That's anabolic. Okay, synthesizing larger molecules from smaller ones in the fed state. Now we have catabolic pathways, right? These catabolic pathways, remember catabolism breaks down things. So these catabolic pathways break large molecules into smaller ones. This is going to be in your fasted state, right? We also call fasted state post-absorptive state. And in a fasted state, this is where your body really taps into storage energy reserves, right? You haven't eaten for a long time. You fasted, right? And so now we got to break down large molecules into smaller ones to get energy. And we'll look into that, right? So that ingested energy, it may be used or stored, right? So ingested molecules, they have three fates, right? We can use it for the energy to do mechanical work. We can use those biomolecules for synthesis, for growth and maintenance of like just general maintenance of our cells. Or we can store it, right? Store it in the form of like glycogen and fat, for example, right? However, we have nutrient pools, right? These nutrient pools are going to be available, right, for immediate use in the plasma, right? So we have a free fatty acid pool, right? We have a glucose pool, which is going to be tightly regulated. And we have an amino acid pool, right? But when we're looking at this glucose pool, right, which is tightly regulated, I want you to understand these terms too, right? Glycogenesis, remember, glyco, right, genesis, right, to synthesize glycogen, right? So glycogenesis means synthesis of glycogen. Lipogenesis, synthesis of fat. Glycogenolysis, lysis, right? Remember to cut to break down. So we're breaking down glycogen, okay? And gluconeogenesis, right? This is where we're synthesizing glucose, right, from a precursor other than carbohydrates. So we're making glucose probably from a fat precursor or a lipid precursor or a protein precursor, such as like an amino acid, right? But we're synthesizing glucose from those things, okay? And so these are going to be your nutrient pools, right? So in your diet, right, you'll be able to take in, fats, carbohydrates, proteins, right? So for example, for proteins, you break those proteins up, right? And there are amino acids, right? So you have these amino acids that's going to be in your blood. However, typically we're going to use amino acids for protein synthesis, right? So we just use those amino acids to build up proteins in the body. Remember when we talked about the central dogma, how DNA gets transcribed into RNA, RNA gets translated into protein, right? And then that translation step, right, that mRNA strand is going to direct the synthesis of this amino acid peptide sequence, right? And those amino acids that's being brought or carried by transfer RNA, this is where those amino acids are going to come from, right? From our diet, right? Now, fat, right? We have a free fatty acid pool. So when we take in fats, we're able to break down fat into free fatty acids and glycerol. Okay, that'll go into our free fatty acid pool. That's going to be in our blood. Okay, and we can utilize this fat for things such as storing it. Right, we can store it in our adipose tissue, right, or we can store it in cells. Or use it for energy, right? That glycerol, right? Remember that glycerol backbone, right? We can use that for metabolism, okay? For carbohydrates, right? We'll break that down into a form of glucose, right? Glucose is going to be our main energy source. Our body typically loves to feed off of feed off of glucose, right? So glucose and our glucose pool, right? This is going to be the normal range, right, of plasma glucose, right? So the body will get it, right? The brain will get it as well, right? So we're in a good position right here, right? If we have too much glucose, we'll start to store it, right, in the form of glycogen. Okay, stored in glycogen, like in the liver, skeletal muscles. But if it is really too much, if we're hyperglycemic, right, you'll start to see glucose in your urine. And then we have some issues with that as well. Okay. Now, notice how the brain metabolism is going to be like below this line right here, below the normal range of plasma glucose. And that's because if it's too low glucose in the body, your brain is going to get it first, right? So your body will sacrifice itself to give that glucose to your brain. Because remember, your brain uses 50% of the glucose that your body has, right? A whopping 50%. Those neurons, your brain needs glucose to provide energy, okay? So this just goes over the different biochemical pathways for energy production, right? For carbohydrate, protein, and fats in a fed and the fasted state. And we know, again, that carbohydrates are going to be typically absorbed as glucose. Also can be fructose and galactose. Proteins are going to be absorbed as amino acids, right? Primarily, plus, we're going to have some small peptides if they're not going to be broken down. And fats are going to be absorbed as fatty acids, triglycerol, and cholesterol. Right, so when we're looking at a fed state, right, so you just ate, right? So we know that carbohydrates will make ATP, okay? We know that glycogen is going to be for short-term storage, and fat is going to be for long-term storage, okay? And we know that the amino acids, they're going to make protein, right, for structural functional proteins, enzymes, hormones, things like that. Okay. However, excess amino acids, they're going to be burned as energy or stored as fat. So just goes over, remember, glucose, right, as it gets into the cell, right, we phosphorylate it, right, with a kinase, right, which is an enzyme that phosphorylates something. That's why we have glucose 6-phosphate now. We can siphon that glucose 6-phosphate into glycolysis. Glycolysis, remember, is the breakdown of glucose, right, in the cytoplasm, right, does not require oxygen, but we are able to produce a little bit of ATP through the process of glycolysis, and as the end result of glycolysis, we're able to make pyruvate. And if we don't have oxygen, it'll go through an anaerobic condition and produce lactate or lactic acid. But if we do have oxygen in an aerobic situation, right, that pyruvate will move into the mitochondria. That pyruvate will then get converted to acetyl-CoA, and that acetyl-CoA will then get siphoned into the citric acid cycle, where we can make a lot more NADHs, a lot more FADH2s, more ATP. Of course, the electron transport chain, right, making a whopping, 32, 36 ATP molecules from that one glucose molecule, right? However, there is another site, right, or there's another source or another pathway that those acetyl-CoAs can go through, right? Those acetyl-CoAs can undergo beta oxidation, right? So fatty acids, right? If your body is using a lot of just fats, right, you'll undergo beta oxidation, okay? And so we'll get into that in just a second. So when we're looking at fat, right, so when we're looking at fat synthesis, right, the transport and fate of dietary fats, right, we can see that, remember, fats are going to come into the body. Typically, they're going to be in like fat droplets because they are nonpolar. They're not going to want to mix with water, right? But they can be absorbed over this intestinal epithelium right here, right? And remember, if they're broken down enough, right, into free fatty acids, right, we can just put that directly into the blood, right, into that fatty acid pool or free fatty acid pool. However, typically, fats are going to be larger molecules, right, and so they're going to be absorbed in the lymphatic system, okay, and from the lymphatic system, then they are able to get into the venous and the blood supply like that, right. But remember, I should go back right here. Remember, it's the bile that's going to be produced by the liver, right, but stored in the gallbladder. But it's that bile that helps to emulsify that fat for it to even get through that intestinal epithelium. And we'll talk about that in the digestive tract too, right? But when that fat gets into the blood, right, so we're able to synthesize our like HDL, right? HDL is high density lipoproteins. We typically get LDL, low density lipoproteins from our meals, right? This is going to be the bad one, right? LDL is the bad one. This is going to be like the good one, basically, right? But the fats that's going to be in the blood, right? These lipids that's going to be in the blood, we have a protein or an enzyme, lipolipase, right, that will break down those lipids into free fatty acids and glycerol. And we can send that free fatty acids and glycerol into adipose tissue, right, and store it like that. So we can reassemble these molecules into triglycerides by the help, of course, of the smooth endoplasmic reticulum, right? Remember, the smooth endoplasmic reticulum synthesizes lipids, cholesterol, things like fats, things like that, okay? And this graph right here shows you the relationship between low-density lipoprotein cholesterol and its increasing risk for developing heart disease, right? So increasing amounts of LDL, right, provides a relatively higher risk for coronary heart disease, okay? So LDL, right, it brings cholesterol from the liver to most cells. However, we call this lethal cholesterol because oxidized LDL in the circulation is going to be taken up by macrophages, and that leads to the development of those atherosclerotic plaques inside blood vessels, right? And however, a high LDL concentration does, that we've noticed, increases a person's risk for cardiovascular disease. All right, or I should say coronary heart disease right here, okay? High density lipoprotein, right, transports cholesterol out of the plasma, right? So this is the healthy cholesterol because we're taking it out of that plasma, right? However, low levels of this is going to be associated with high risk of developing coronary heart disease as well, right? So abnormal plasma levels of lipids, right, increases the risk of atherosclerosis and coronary heart disease, right? So high LDL or low HDL, right? So remember, fats, right, or these lipid-based molecules, they are a good indication for like predictors of heart disease, whereas we'll talk about glucose, right? Abnormal levels of glucose, and that's going to be like predictors of like diabetes mellitus, like a sugar type of pathology in the body, right? So in a fasted state, metabolism, remember, fasted state is catabolic, right? We're breaking down things, right? So for example, we're breaking down glycogen into glucose via a process of glycogenolysis, right? Proteins can also be used, right, to make ATP because we can deaminate a protein, like take that amine group off. And when you take that amine group off, you're creating an amine group plus an organic compound, and it's that organic compound that can then be siphoned into making into glycolysis, right? Lipids, remember lipids, they're going to store more energy than glucose and proteins, right? Lipids break down through lipolysis, right? You break that lipid down, right, into that glycerol and that free fatty acid, right? That glycerol backbone, that can be siphoned into glycolysis. But that free fatty acid, right, strand, that can undergo beta oxidation, right? And it can produce those acetyl-CoA groups that I was mentioning earlier, right? And so excess acetyl-CoA becomes ketone bodies, right? Or ketones for short, or even keto acids, right? However, these are strong metabolic acids that could lead to ketoacidosis, right? So in a fasted state metabolism, right, we must maintain plasma glucose homeostasis for the brain, right? You haven't eaten, you fasted. We must maintain plasma glucose homeostasis, especially for the brain, okay? So we know that the liver, right, in a fasted state, we're going to break down glycogen into glucose, okay? So we're breaking down glycogen into glucose via glycogenolysis, right? We have our adipose tissue, right? The lipids become free fatty acids and glycerol, and that's going to enter the blood, okay? And it's, again, it's in a fasted state. You haven't eaten for a while. Your muscles, right? The glycogen in your muscles can be used for energy. Muscles also use fatty acids and break down their own proteins to amino acids that then enter in the blood, right? However, your brain, remember, glucose is the true source of energy for your brain. Your brain loves glucose, right? And it uses 50% of the glucose that your body has. However, the brain can use glucose and ketone bodies. It wants glucose, but in the absence of glucose, it's going to use these ketone bodies, okay? And so let's hit on that for a second about beta oxidation, right, and these ketones, right? So in the liver, right, if fatty acids are broken down to produce acetyl-CoA faster than they can be siphoned into the citric acid cycle, right, those excess acetyl units, they're going to become ketone bodies. Ketones are these chemicals made in your liver, right? You produce them when you don't have enough of the hormone insulin in your body to turn that sugar or that glucose into energy. So you need another source. So your body uses fat instead. And it's your liver that's going to turn this fat into ketones. And these ketones, or these keto bodies, right? Keto acid bodies, right? These are going to be a type of acid, right? And that's going to be sent into your bloodstream. So during beta oxidation, these free fatty acids are broken down into acetyl-CoA and these ketone bodies. The level of ketone bodies in your blood will increase when high levels of fatty acids are being metabolized over and over, right? So the process of breaking down fatty acids into acetyl-CoA and ketone bodies, again, we call this beta oxidation. Remember that, okay? And these ketone bodies become a significant source of energy for the brain in case of prolonged starvation, right? So when glucose levels are low, right? However, we know that these ketone bodies, as they enter the blood, they are called keto acids for a reason, right? So they can create a type of metabolic acidosis, right? And that could lead to eventual problems, right? So let's look at the homeostatic control of metabolism, right? So metabolism is going to be controlled primarily by the ratio of insulin to glucagon, right? In a fed state, you just ate, right? Insulin will dominate, right? Because you just most likely took in sugar. So remember, insulin's job is to reduce blood glucose. In a fasted state, glucagon dominates. And remember, you haven't eaten for a while, so you're gonna probably most likely have low blood glucose levels, right? What is glucagon gonna do? Glucagon is gonna work to raise blood glucose, okay? Remember, these are the hormones that will regulate plasma glucose concentrations. Again, insulin reduces the insulin, remember, produced by those beta cells in the pancreas, okay? Via those the islets of Langerhans cells, right? Insulin is produced by beta cells, okay? This is the hormone that's produced by beta cells that's helped to reducing blood glucose levels. However, glucagon, right, is a hormone that's produced by the alpha cells in the pancreas. And glucagon, when secreted, it helps to raise blood glucose levels, right? And so you can see, right, in this graph right here, right, glucose, insulin, and glucagon levels before and after a meal. So let's look at insulin first, right? So insulin levels are going to be low because this right here, right? This is like the end of your fasted state, right? And now you just ate a meal, right? So now this is, for example, the first meal of the day, okay? And so you're gonna have an influx in sugar, right? Influx in plasma glucose concentrations. So you're gonna start producing insulin to reduce the blood glucose levels, right? And now, however, glucagon on the other hand, right? Glucagon is gonna dominate that fasted state. So this is the fasted state, right? And this right here, after you ate that meal, right? This is the fed state. So glucagon is going to decrease in numbers. Because why? Because your glucose levels are high, right? We don't need to raise the blood glucose levels anymore, okay? So I just wanted to bring this image back up too, right? How insulin is secreted by the beta cells, right? So remember, insulin is going to be secreted by the beta cells in response to high glucose levels in the blood, okay? So remember that when there is low glucose, right? So this is your beta cell that produces insulin. When there's low glucose, right? There's little bits amount of glucose, right? So we have a decreased metabolism, which ultimately means we have a decreased amount of ATP being produced. And we have this potassium ATP leak channel right here. And so this channel stays open, right? And potassium just leaks out, just randomly, just regularly leaks out, right? So the cell is at a resting membrane potential, right? However, we notice that because it's at a resting membrane potential, these voltage-gated calcium channels are closed, right? And these insulin, right, they remain in these secretory vesicles. However, when now we have high plasma concentrations of glucose, glucose will enter that beta cell, right? Undergo metabolism via glycolysis in the citric acid cycle. We're going to be able to produce more ATP, and it's the ATP that binds to this potassium leak channel that closes it, okay? And once ATP is bound, closes this potassium leak channel, this potassium stays in the cell because it can't leave now, right? So we have a higher amounts of positive charge staying within that cell membrane. So remember, if it's positive, 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 positive staying in there, the cell is going to depolarize, right? Get less negative, get more positive, right? And this change in the membrane, right, then opens these voltage-gated calcium channels, right? Because there was a change in the membrane potential, there was a change in charge, right? And these voltage-gated channels, they're going to open, right, in response to a change in charge, okay? So as potassium stays within the cell, right? That changes the membrane potential. It depolarizes it. It gets less negative. That makes these calcium channels, these voltage-gated calcium channels open. Calcium then gets into the cell. Calcium is going to act as an intracellular signal, right? To direct the exocytosis of these vesicles that contains the insulin, right? So calcium triggers, right, exocytosis, and now we have insulin being released into the blood, okay? So this is how insulin is released, okay, in response to high glucose levels, okay? So insulin is the dominant hormone in the fed state, right? So insulin will promote anabolism. There's factors that control or will stimulate insulin secretion, right? Of course, increased plasma glucose, right? Even increased plasma amino acids, right? So insulin will be released when there's a lot of sugar in the blood and when there's a lot of amino acids in the blood, right? The other factor that will control or stimulate insulin secretion, right, is going to be that feed-forward mechanism, right? That feed-forward effects of those GI, of those gastrointestinal, right, hormones, right? And so recently it's been shown that as much as 50% of insulin secretion is actually stimulated by the hormone glucagon like peptide 1. That's this one right here, right? And so this protein or this enzyme, right, is going to be important, right? We also have the GIP, which is the gastric inhibitory peptide, right? Both of these are going to be incretin hormones, and they're going to be produced by cells of the ileum and the jejunum in response to like nutrient ingestion. So the incretins, they're going to travel through the circulation to the pancreatic beta cells and may reach them even before the first glucose is absorbed. And so this anticipatory release of insulin in response to these hormones prevent a sudden surge in plasma glucose concentrations when the meal is absorbed, right? And so there's also other GI hormones such as cholecytokinin, gastrin, that's going to also amplify insulin secretion. Okay? Looking at the parasympathetic activity, right? Parasympathetic activity, we're going to stimulate insulin secretion, right? Whereas the sympathetic activity, insulin secretion is going to be inhibited, right, by those sympathetic neurons. So in times of stress, right, the sympathetic input to the endocrine pancreas will increase, right? That's going to it's going to be reinforced by those catecholamines released from the adrenal medulla. And so the epinephrine and the norepinephrine will inhibit insulin secretion and switch metabolism to gluconeogenesis to provide extra fuel for the nervous system and skeletal muscles, right? If you need to go, you don't want, you want to be able to have that energy, right? And utilize that glucose, okay? So glucagon, right, is dominant in the fasted state, right? Glucagon is antagonistic to insulin, obviously, again, secreted by those alpha cells in the pancreas. Glucagon works to prevent hypoglycemia. It works to prevent low blood glucose levels, right? So again, it's going to raise blood glucose levels, okay? And the liver is going to be the primary target, okay? So insulin promotes anabolism, right? So let's get back to insulin for a second. So how does insulin promote anabolism? Well, insulin is going to lower plasma glucose in the following 4 ways. Insulin increases glucose transport into most, but not all, insulin-sensitive cells. It's also going to enhance utilization and storage of glucose, and we'll talk about that in a second. Also, insulin will promote fat synthesis, right? It is also going to enhance utilization of amino acids. Okay, but I want to talk about number 1 and 2 too, right? So again, insulin, right, increases glucose transport into most, but not all, insulin-sensitive cells. And when I say insulin-sensitive cells, that just means they have a receptor for insulin on there. Okay, so in adipose tissue and in resting skeletal muscle tissue, right, we can see in this fed state, insulin signals the cell, right, to insert these GLUT4 transporters into the cell membrane, right? So notice how insulin binds, right, to its insulin receptor on the cell membrane. It creates a signal transduction cascade that will tell, right, this vesicle to undergo exocytosis to put these GLUT4 transporters within the cell membrane. Remember, these GLUT transporters, they help to transport glucose, okay? So notice how these GLUT transporters, they're not automatically in the cell membrane. They're actually in vesicles. And in the presence of insulin, right, then they get put into the cell membrane. And then when those GLUT transporters are put into the cell membrane, now glucose can enter the cell, okay? Again, this is in the adipose tissue and muscle tissue, right? So, as we see here, adipose tissue and resting skeletal muscle, right, they require insulin for glucose uptake. Now, without insulin, their GLUT4 transporters, right, these GLUT4 transporters, right, they're withdrawn from the membrane, right, and they're stored in these cytoplasmic vesicles, okay? This is an example of membrane recycling, though. But when insulin binds to the receptor and activates it, those the resulting signaling molecule, right, or signaling transduction cascade, excuse me, causes the vesicles to move to the cell membrane and insert those GLUT transporters via exocytosis. And again, we know that through facilitated diffusion, right, glucose can be uptake, okay, from that interstitial fluid. Now, interestingly enough, right, exercising your skeletal muscles, right, so exercising skeletal muscles is not dependent on insulin activity for its glucose uptake. So when muscles contract, these GLUT4 transporters are inserted into the membrane, even in the absence of insulin, and glucose uptake increases. So the intracellular signal for this complex it seems to be complex, right? But it appears to be involved with calcium. Calcium seems to be involved, right? As well as a variety of intracellular proteins. Okay. Now in the liver, right? We know that insulin enhances utilization and storage of glucose. Now remember, I just want to point out though, in adipose tissue and in skeletal muscle tissue, we have GLUT4 transporters, right? And in the liver, we have GLUT2 transporters. Notice how these GLUT2 transporters are automatically already within the cell membrane. Okay, so glucose transport in liver cells, right, with these hepatocytes, right, is not directly insulin dependent, but it's influenced by the presence or the absence of insulin, right? So again, these liver cells, they're going to have these GLUT2 transporters that are always present in the cell membrane. So in a fasted state, right, when insulin levels are low, glucose moves out of the liver and into the blood to help maintain glucose homeostasis. Now, in this process that we see here, right, notice how insulin will bind. It's the binding, right, of insulin to that cell receptor for insulin that's going to signal or provide a signal cascade, right? So what happens is this makes it signals for a kinase, right? It signals for a specifically hexokinase, right? And that's going to phosphorylate glucose into glucose 6-phosphate. And so now we're changing it, right? We're changing this glucose that's coming into the cell. Now it's not glucose anymore. Now it's glucose 6-phosphate. And so because now it's glucose 6-phosphate, right, that helps glucose continue to move down its concentration gradient. Because remember, in a fed state, glucose concentrations are high in the extracellular fluid, right? They're high. So, and remember, through facilitated diffusion, right, they're going to want to go from an area of high concentration to an area of low concentration. But if we continue to tag these phosphates onto these glucoses, we're changing it. That glucose now is glucose 6-phosphate, helping continuing to drive that glucose down its concentration gradient into the cell, right? From the extracellular fluid to the cell, inside the cell. Now, in a fasted state, we know that glucagon is dominant, right? So let's look at a fasted state in adipose and in muscles, right? So, again, that you haven't eaten for a while, right? There's low glucose, okay, in the blood. So in the absence of insulin that we can see here, right, there's no insulin binding, right? There's no GLUT4 transporters in the membrane, okay? Remember, you needed insulin to bind to signal this vesicle to tell them to put those GLUT4 transporters on the membrane. But if there's no insulin, those GLUT4 transporters, they're going to remain in those cytoplasmic vesicles. Now, in a fasted state in the liver, right? And so these hepatocytes, they make glucose and transport it out into the blood using these GLUT transporters. Because remember, these GLUT transporters are always within this cell membrane in a hepatocyte, right? Okay, and these are, again, facilitated diffusers, right? So glucose is going to want to move down its concentration gradient. So if it's low glucose in the blood or the extracellular fluid, and it's high inside the cell, right, especially in a liver cell, it's going to be glycogen, right? Glycogen stores up glucose. So glycogen will get broken down via glycogenolysis, right, into glucose, and now we have high concentrations of glucose inside the cell, and it's going to want to diffuse outside the cell, right, where it's low at, okay? But again, not responding to that insulin right there, right, because the cell membrane already has these GLUT transporters, right, and these are facilitated diffusers where the glucose will just run down its concentration gradient. Okay, this is just the endocrine response to hyperglycemia, right, and hypoglycemia, right? So in diabetes mellitus, right, these are going to be a family of diseases, right? Diabetes mellitus is going to be characterized by abnormally elevated plasma glucose concentrations or hyperglycemia resulting from inadequate insulin secretion or abnormal target cell responsiveness or even both, right? And unfortunately, complications of diabetes will affect blood vessels, eyes, kidneys, and the nervous system. So we have two types of diabetes, right? So type 1 diabetes, we characterize it by insulin deficiency, and that's going to be from an autoimmune destruction of your beta cells. And remember, the beta cells produces insulin, but if these beta cells are destroyed, no insulin will be released, right? This is typically like a genetic-based type of diabetes. Now, type 2 diabetes, mellitus, is characterized as insulin-resistant diabetes, right? And so your body doesn't respond to insulin like it normally should. Now, insulin levels they could be normal or even elevated initially, right? However, over time, they can become insulin deficient. And so typically we used to identify this as adult onset, but we're noticing that adolescents are becoming type 2 or becoming a person with type 2 diabetes, right? And so type 1 diabetes, right? These individuals are going to be prone to ketoacidosis, right? So again, in type 1 diabetes, no insulin is being released, right? No insulin is being released. And so we have increased plasma glucose levels, right? And so I won't focus on the amino acids or the fatty acids, right? But I will focus on like the complications due to glucose, right? So what happens is, right, in type 1 diabetes, no insulin is being released because we have a destruction of those beta cells, right? And so as a result, we have decreased glucose uptake, okay, in like your muscles and your adipose tissue, right? And as a result, we also have a decreased amount of glucose utilization, right? And so your brain interprets that as starvation, right? And then that leads to polyphagia, right? And that's going to be where you eat a lot because your brain is saying, okay, well, you're not taking in glucose, so let's eat, right, to make up for it, okay? So because the insulin is not there to allow, to reduce blood glucose levels, right? Insulin really just acts as a key to open up the cell to say, hey, okay, let the glucose in, right? That we just saw in those processes. However, if insulin is not there, blood sugar is going to increase. That's going to lead to hyperglycemia, right? Too much blood glucose concentration or too much sugar in the blood, basically, right? And if it's too much sugar in the blood, then that's going to exceed renal threshold for glucose, right? And we'll talk about this when we get to the urinary system, though. But if it's too much glucose, right, you're going to start seeing it in your urine, right? And this is where you have glucosuria, right? And that's glucose in your urine. And so you're going to start peeing out more glucose. And because you are peeing out the solute, right, you know water wants to follow, right? That's why you have that osmotic diuresis, right? And polyuria. So you're peeing out more and more and more because you're peeing out more sugar. And water will follow that solute. And if you're peeing out so much, right, that's going to lead to dehydration, right? And dehydration, your hypothalamus is going to say, okay, well, let's stimulate thirst, right? And so that's going to lead to polydipsia, right? And that's just constantly drinking, right? And you can think of polydipsia as where you're constantly dipping your cup in water, right? It's also, that dehydration is also going to stimulate ADH being released by the hypothalamus and released via the posterior pituitary gland, right? And again, ADH, or also called vasopressin, right? That's going to go to the kidneys and tell you to say, hey, let's retain some of this water, right? So it's an antidiuretic, right? Antidiuretic hormone. So it's going to say, let's retain some water, okay? Let's not lose any more water, any more volume that we've already lost. But as a result, because you lost so much, right, you're going to have a decreased blood volume, right? And that decreased blood volume is directly associated with decreased blood pressure, right? Now, you will try to compensate for it, right, by your cardiovascular centers, cardiovascular control centers, and your medulla is going to say, hey, let's try to control this. However, that could lead, if we don't compensate correctly or compensation fails, that can lead to circulatory failure, right? That can also then lead to anaerobic metabolism, and anaerobic metabolism will lead to lactic acid production, which is a form of metabolic acidosis, right? You have metabolic acidosis, you're going to start ventilating, right? Start breathing more of that CO2 out of your lungs, right? You're going to see your urine that's going to be acidified, and you're going to have a lot of potassium in there as well. Unfortunately, also, because you're not utilizing glucose, those ketones, right? Those ketone bodies will increase. And if you have too much ketones, we know that that can lead to ketoacidosis, right? Ketoacidosis can also then lead to metabolic acidosis, which can ultimately lead to coma or death, right? So that's how a person with type 1 diabetes can lead to dehydration that we see and metabolic acidosis, okay? Type 2 diabetes, right? This is often going to be elevated. A person with type 2 diabetes often have elevated insulin levels, right? Because their body's just not responding to it because they're insulin resistant, right? So their sensitivity to insulin has decreased, right? Now, type 2 diabetes is going to account for 90% of all cases of diabetes, right? And really this epidemic is going to be attributed to our sedentary lifestyle, ample food, and overweight and obesity, right? Again, it's going to be characterized by insulin resistance. And so we're going to have complications that's going to include atherosclerosis, neurological changes, renal failure, and even blindness. However, the first line of therapy, right, should be exercise, weight loss, right? Exercise, weight loss, things like that can definitely help, right? Especially with type 2 diabetes, okay? Now, you can also use drugs too, right? You can use drugs for treating diabetes, right? So there are certain drugs like the sulfonylureas, right? They will stimulate insulin secretion. So those type of drugs, for example, they will bind to the potassium ATP channel in the beta cell and close it, right? And that's going to lead to a depolarized cell, and that's going to, of course, lead to the results, right, of the calcium influxing into the cell, things like that, right? But first, therapy should be exercise and weight loss, right? Now, when diagnosing diabetes, right, so typically what they'll do is they'll use a fasting individual, right? You'll have you fast, right? So like maybe, for example, overnight you don't eat, right? And then you'll drink, some juice in the morning, right? And so in a normal patient, yeah, you're going to have a rise in blood glucose levels, right? But then that's going to soon decline, right? Because you're producing insulin, and your insulin is being taken up and allowing it to reduce your plasma glucose levels. Now, in individuals with diabetes, we know you give them a cup of juice, their sugar goes up, and it stays elevated, right? It stays elevated, okay? Now, metabolic syndrome, right, it links diabetes and cardiovascular disease. So it's going to be a combination of type 2 diabetes, obesity, atherosclerosis, and high blood pressure. So diagnostically, you must have at least 3 of the following, right? Central or visceral obesity, right? So like a large waist circumference, like so over 40 inches for a male, over 35 inches for a female. Your blood pressure is going to be more than 130/85, right? Fasting glucose or fasting blood glucose is going to be more than 110, right? Elevated fasting triglyceride levels are going to be high, right? And we have a low plasma HDL levels, right? So these 3 of these can lead to metabolic syndrome, okay? And that can lead to, again, cardiovascular disease. Right now, there's going to be multiple hormones that influence metabolism, right? The regulation of metabolism is not completely understood, though, but we know that we have that neuropeptide and those hypothalamic hormones that's going to be involved in hunger, satiation. They're going to have their metabolic effects. We know the thyroid hormones of their cortisol pathway, growth hormone, epinephrine, they're all going to play an effect to influence metabolism. Now, let's change gears to regulation of body temperature. All right, so humans, we have a homeothermic temperature regulation, right, within narrow ranges, right? So we can't get too hot or get too cold. So the body temperature balances heat production, heat gain, and heat loss, right? So heat input, which is gain, right, would be, external heat input, right, from the sun, things like that, or even internal heat production from, contraction and just cellular metabolism and processes. Heat output is where we lose heat, right? Conductive heat loss, radiant heat loss, evaporative heat loss, you sweat and you have that heat loss being carried away through your sweat, right? So normal metabolism generates enough heat to maintain body temperature, right, in our thermal neutral zone. So about 30 degrees Celsius, okay? Now about above that thermal neutral zone, we must compensate for that heat gain, and below we must compensate for that heat loss, right? So we have these thermal regulatory centers that's going to be located where? In the hypothalamus. And we also have thermal receptors in the skin and the interior hypothalamus. So we can alternate or provide alterations in our cutaneous blood flow to conserve or release heat, right? And our sweat also contributes to heat loss. So if you look, right, we have unregulated heat production, which is like voluntary muscle contractions, normal metabolic pathways, even regulated heat production, right? Like shivering thermogenesis or even non-shimmering thermogenesis, right? So high environmental temperatures, really, really, really hot. You're going to vasodilate your cutaneous blood vessels, right? You're also going to try to increase sweating, right? Of course, behavioral responses, remove clothes, staying out of the sun, things like that. And if it's too cold, right, you'll try to vasoconstrict, right? So don't have so much blood vessels or blood, I'm sorry, going to those areas, right? You want to conserve that blood because heat travels in blood. So you want that heat to go to your organs. So typically you're going to find like your fingers and your toes, right? They're not going to be getting a lot of blood, thus a lot of heat. And that's why you'll see like toes and fingers becoming frostbitten in certain situations like that, okay? But yeah, that was just looking at the chapter of metabolism and energy balance, okay? Let me know if you guys have any questions, okay? Enjoy.